Thank you very much. So thank you for having the opportunity to speak here. So I'll tell you about some joint work. It's primarily with my PhD student, Andres Duquara, where we started a couple of years ago. And more recently, we have a paper with Francesco Buscemi, Valerio Scarani, and his student, Peter Sidajaya. And my hope today is to give you kind of an overview of this research project that we've started and highlighting just kind of some of the main results. So just to set the stage, so obviously we're all very used to Alice and Bob in quantum information. I think it's fair to say we take them for granted, but they are very useful to have these agents who make decisions. And in particular, we know, most of the tasks that we consider, we think about optimizing some figure of merit or some cost function, such as, state discrimination or query complexity or thermodynamics. And so using agents is helpful to frame this, but we can use it in one kind of slightly different way. And in particular, we know that we always have uncertainty in quantum mechanics and in quantum information. And with that uncertainty, in principle, might come some kind of risk. And the kind of starting point for this research project is to ask a very simple question, which is to say, if we take into account the fact that Alice and Bob might have some attitude towards risk, they might have some risk aversion, can we take this into account in some kind of principled and disciplined way? And is it an interesting thing to do? And is it a useful thing to do, right? And what I would like to try and convince you over the next 20 minutes is that maybe the answer to this is yes, I think it is. But this is only the start, and I think this is something interesting, right? So the idea, kind of the big picture, is that we've had a long history now of combining information science and quantum physics. And so we're questioning to what extent bringing in ideas from the theory of economics, and in particular, one kind of undergraduate topic is called expected utility theory, which I'll explain. We think that this is helpful to bring this in, and altogether we get some new insights into some old problems. Okay, so just a quick outline. So I'll start off by giving an introduction to this bit of economics, expected utility theory. I expect most people unfamiliar of this, or maybe have only heard very basic aspects. So I'll introduce what I need. And then I'll tell you briefly about two applications, the two we've found so far. So one of them is in a new task, which we call quantum state betting, which is a pretty natural generalization of state discrimination. And the second one is in kind of stochastic or quantum thermodynamics. So you can pick whichever one you prefer. And I'll finish by giving you some kind of outlook on what I think are the interesting future directions of this research program. Okay, so let's jump into expected utility theory. So the main idea I need to introduce is the idea of a lottery, right? So this is going to be, I can model this by some random variable x being the outcome of the lottery. And what I need to introduce to make it interesting is some kind of bookmaker who's going to offer me some odds on this random variable, right? So they offer me odds, say OX for 1, meaning that if I place some unit bet on the outcome little x, and that is the result of the lottery, then I will walk away with O of X pounds, right? And so this is the task that I want to consider, or a general type of task. And so now our agent, Alice or Bob in this case, we all think about them as now being a gambler. And so they have some wealth that they can use to gamble with, and we'll assume that they bet some proportion of their wealth, B of X, on the outcome of the lottery being little x, right? So in principle, they can spread their bets. They could bet on all the different outcomes if they wanted to, and this is the kind of general scenario we'd like to consider, right? And what we would like to do is we don't want to consider a single lottery. It turns out it's interesting to actually think about comparing different lotteries. And so this, one final thing. So what you might say for a given lottery, the figure of merit you might want to consider is, say, the average winnings, the average return at the end. But what we're going to see is that this is not actually the quantity that I'm going to focus on in this world where I have a attitude towards risk. So now, as I wanted to say, so we want to consider comparing lotteries. And to keep things simple, I'm going to consider two very simple lotteries that will hopefully get the main idea across. So lottery 1, let's imagine I have a fair coin, which is flipped. And now the bookmaker offers me these odds. So if it comes up heads, they offer me £100 return. And if it comes up tails, I get nothing, right? So this is kind of lottery number 1. And in general, I want to compare this to another lottery, and I'm going to compare it to a really trivial type of lottery, which is going to act as kind of a good reference with which I can compare any lottery to. And this is a deterministic lottery. So I could phrase that as there's a perfectly biased coin, so it always comes up heads. And when it comes up heads, I'm offered £30, right? So in some sense, this isn't really a lottery at all. This is kind of me being offered the possibility to walk away from this lottery. So I can just walk away with kind of £30 in my back pocket, or Alice or Bob can. And I should say, I mean, in both of these cases, because I've set it up very simply, and I did this on purpose, that in both cases you should always bet on heads, right? In no case does it ever make sense to bet on tails. So in this case, I've got this. I'm going to walk away with nothing or £100. In this case, I always walk away with 30. And the basic question we would like to ask is, which one would you choose, right? Or which one would Alice or Bob choose? And this is not a trivial question in the sense that these two lotteries have kind of very different features, right? So on the one hand, if we think about the first one, it has a higher average return of £50, but there are these huge fluctuations. I walk away with nothing or I walk away with 100. Whereas the second one, there's no fluctuations, but I always walk away with £30, right? And so the point is, for some rational agents, they might actually prefer lottery 2 to lottery 1, even though it pays out less on average, right? And if they would still prefer lottery 1, well, maybe I'll tweak lottery 2. Maybe I'll put this £30 up to £40, right? And at some point, if I keep on tweaking lottery 2, I could probably make lots of people walk away with an amount which will be lower than the average, right? And the reason we do this is because it's very rational for people to have a aversion to risk, and they would rather have less money with certainty than, say, more money on average, right? And so this is what expected utility theory allows us to do. It allows us to model agents who have an attitude to risk, and where it would then become rational for them to choose lottery 2 over lottery 1, right? And this is what we want to incorporate into Alice's and Bob's decision-making process, right? So let me just try and formalize this intuition a little bit about how would I make this preference. And the way this is done is with a so-called utility, introducing a notion of utility. So gamblers, Alice or Bob, will now have some concept of utility, which, if you want to think about what this might mean, you can think about this as being a proxy for your happiness or your satisfaction, right? And I like to think about this as a kind of renormalization of wealth to account for my attitude towards risk. So kind of my satisfaction with wealth will not grow linearly with wealth. It's going to grow in a different way. And in particular, each utility has a utility function. And a typical utility function is going to look like this. So it's going to be a concave type of function. And in particular, when you're risk averse, it turns out that your utility is not going to grow linearly with wealth. It's going to grow sublinearly. So you're going to get this concave shape. This is a typical type of utility function for someone who's risk averse. Okay, and let's try to understand why and how this makes sense of what I had in the previous slide. So let's imagine this one outcome. I had £100 was one of my returns. This gives me some amount of utility, U of 100. The other outcome was to get nothing, and that gives me some U of 0. And so now I can ask, well, what is the average utility that lottery 1 gave me? So it was a 50-50, so it's going to be right in the middle here, right? So this is the average utility of lottery 1, and in some sense, this could be a kind of a way of quantifying lottery 1 through this average utility, right? And so what we can ask is we can ask a nice question. This is what the economists do, is they say, well, what is the amount of wealth which gives me exactly the same satisfaction as I get on average from this lottery, right? So we just kind of work backwards, and this is the so-called certainty equivalent wealth. This is the amount of wealth that someone could give me, which gives me exactly the same satisfaction or same utility as I would get on average from lottery number 1, right? So this is what we can infer from this. This is what we use this utility function to do, basically. And in this case, the average, which was 50, is actually higher than the certainty equivalent, right? So this is the all-important bit, and I'll come back to this just in a second, is we have this interesting behavior where this certainty equivalent comes out to be lower than the average. Okay, so just more formally, if you think, what is this WCE? It's just the inverse of the utility function applied to the average of the utility. So this we can calculate in general. And crucially, this determines actually the boundary between the preferences, right? And so what do I mean by this? So I mean that now in this lottery 2, I had this £30. So if I call that W debt in general, so if I offered you some amount which is lower than this certainty equivalent value, then you will actually go for lottery 1. You'll pick the gamble because the amount I'm going to offer you gives me less satisfaction than I got on average from lottery 1. So lottery 1 is preferable, it has more expected utility, right? Whereas on the other hand, if I offer you any amount larger, then now I'm going to get more satisfaction from lottery 2, from walking away with this deterministic amount of wealth. And so I'll swap my preference from lottery 1 to lottery 2. And as we see, the fact that I'm risk averse tells me that can be this gap, this kind of deficit, where there's this interesting regime, which is the one right here, where I'll walk away from the bet with less than the average return of the bet. And I will do that rationally, and and this is this behavior here, okay? And so just to say, so the central tenet, if it hasn't become clear, of expected utility theory is that what people do is they maximize their expected utility. So this is a way of modeling the way agents behave. So not the average wealth. And it will turn out to be useful in this work is to actually rephrase things, not in terms of the expected utility, which is this kind of abstract quantity, but actually to work instead in this more physical quantity, which is this certainty equivalent wealth. Has the right units at the very least, but this is still a quantification of lotteries. So if I have your lottery, I can tell you what is, given my attitude towards risk, I can tell you what is my certainty equivalent wealth. This is a rational way of associating a value to a lottery, which tells me how much would you have to offer me to make me walk away from this bet, right? Okay, so one more slide on the basics of expected utility theory. So what was this utility function? Well, in general, there's actually infinitely many different utility functions that you can play with, and the economists play with lots. And each one would actually specify a different attitude towards risk. So there would be a different agent that we'd be modeling with this function. But there are actually two very simple kind of idealized attitudes towards risk, which I like to think of as being like the harmonic oscillators of economics, because these model very idealized agents, and they're very nice and to play with. And so these were the two which are going to arise in our results in a minute. So the first one is called having a so-called constant relative risk aversion, or also in that jargon is the isoelastic utility. Looks similar to a function that appeared in Christoph's talk a couple of talks ago, if you're in the room. So it has this particular form. The form is really not so important, but I just want to tell you that there is this so-called type of attitude towards risk. And what does it mean to have constant relative risk aversion? Well, it means that if I take my lottery and I actually kind of scale up all of the values by some value alpha, so instead of 0 and 100, I gave you 0 and 1,000, it turns out that the value of that lottery, the certainty equivalent wealth, according to this gambler, would also just scale by the same factor, right? So this is not true for all gamblers, but it happens to be true. If this is your attitude towards risk, then you have this very nice kind of physical property. The other type of attitude towards risk, which is very natural and common, is a so-called exponential utility, or equivalently, a constant absolute aversion to risk. And it has this form with an exponential now. And sorry, I should say, in both cases, you actually get one parameter families of attitudes towards risk, sorry. So this R parameter, this is exactly there's one parameter left, and this tells me how risk averse I am. So if I have a larger value of R, I'm more risk averse. If I have a smaller value, I'm less risk averse. And similarly for this little r for this exponential family. And in this case, now it's instead of scaling up by a factor, this one is where I just shift by a constant, right? So if I just have 0 and 100 and I go to 10 and 110, and I considered that lottery and I had this constant absolute risk aversion, then the certainty equivalent would just increase by the shift in this case, right? So these are just two very natural, hopefully you see these are kind of very natural properties to have, right? So this is all the basics of expected utility theory I need. And now we can use this to hopefully, I want to convince you that this idea is useful in quantum info. Okay, and so the application number one is in a new generalization of quantum state discrimination, which I'll call quantum state betting. So we have our lottery from before, where we had some random variable rho of x, but now we kind of consider giving you quantum side information, or in other words, I have my random variable and I have my quantum state rho of x, right? And in this context, rho of x is really like side information about the lottery that I have, right? But you can see that the object we're considering is still just an ensemble of states. So really this is like quantum state discrimination. So as in the lottery on the previous slide, I'm going to have my bookmaker offering me some odds, O of x for 1, exactly the same. And so now as a gambler, if I'm going to play quantum state betting, so what can I do? Well, of course, I've got quantum states, so I can measure them using some POVM. And now once I've got the outcome of my measurement, I can place a conditional bet, right? So I can place different bets on what I think is the state, conditional on what the outcome of my measurement was, right? Which is very natural. In state discrimination, you measure and then you make a guess. Here we're measuring and then now we're kind of spreading our bets across the different states, right? And so we want to take into account that our gambler, a risk-averse agent playing this state betting game. And so our figure of merit is then going to be certainty equivalent wealth in this task, right? And so we'll consider an agent with a constant relative risk aversion. So the first of the two types of agents I had on the previous slide. And we're going to consider the maximized isoelastic now, because it was constant relative risk aversion, certainty equivalent wealth. And so formula is not overly important, but it turns out to be this formula here, right? So everything is fixed. So it's for a fixed measurement, a fixed game, a fixed set of odds from the gambler. And the only thing I'm going to allow myself to optimize on this line is just my betting strategy, right? So this is our quantity. And say our first result, which is then easy to see, is that this quantity, once you do this maximization, has a very nice form. And it turns out it's a so-called conditional Renyi divergence, right? So I guess Renyi divergences are much more common, as we saw 2 slides ago, but you can actually also consider conditional versions. And it turns out that this quantity turns out to be such a divergence of Renyi type. So what is this R of x? So this is actually a probability distribution, which is induced by the odds. So it's just 1 over the odds turned into a probability distribution. And these are so-called fair odds. And so what is the particular form of this conditional Renyi divergence? So this is all purely classical, so there's no complications yet, like we saw 2 talks ago, but it has this particular form here. So again, not overly important, but maybe the experts in the room might find this form interesting. But kind of what's cool about this result, one thing I really like, is that our Renyi parameter, alpha, is purely specified by this R, and R was exactly my attitude towards risk, right? So now I'm giving the Renyi parameter a real operational interpretation. So it is exactly the same thing as quantifying my agent's attitude towards risk, right? So I found this particularly nice. Okay, thank you. That we get this operational interpretation. Okay, so there's a couple of corollaries. So if the bookie is very stupid and offers me constant odds, then everything simplifies and I get a much more usual expression. I actually just get a conditional Renyi entropy plus a log term, which is very nice. So this is, say, a very simple corollary of the previous result. And actually, if I go back to where we started chronologically, we found it very interesting to compare this value of state discrimination when I have the kind of side information relative to the case where I take that side information away, in which case I'm back to the bare lottery, right? It's just a random variable which I'm placing bets on. So if I take away the state's rho of x, or I don't allow you to perform a measurement, you can also think, well, what was the value of the lottery in that case? And I can really compare, can ask what was the kind of value of the quantum side information to this agent based upon given that they have this risk aversion. And so what we find is if we look at this ratio between the certainty equivalent wealth when I have the side information to when I take it away, okay, I need to take a log. I actually then get the difference of these two, I get the conditional Renyi entropy minus now just the standard Renyi entropy for a single variable. And this difference was well known in the literature. It's the Renyi-Aramoto mutual information of order, again, alpha being 1 over R, right? So this is what we find. And we like this result because actually this can be really viewed as a generalization of a kind of a whole sequence of results which have appeared over the last few years, which have related discrimination tasks with the generalized robustness, which is nothing but the max relative entropy, right? So again, maybe just for the experts in the room, this can really be seen now as a generalization to all values of alpha of this task, right? Which we found very nice. So given the time, I'm going to have to go a little bit quickly in the next bit, but I will just switch gears slightly and talk very, very quickly about quantum thermo. So the kind of situation we want to consider now is that I'm doing some kind of process to extract work from some system, so some gas in a piston, which does some work on charges or discharges a battery. We have our second law of thermodynamics, which tells me how much work I could do in principle. And it's kind of useful to think about how far I am from being perfect. So in other words, how much work do I lose or dissipate in this process? Is the amount of work I actually get or spend relative to what I should have done, right? So this is kind of classical thermo, traditional textbook. And if we go to a more quantum setting or a kind of just a stochastic setting, then the amount of work I get now becomes a random variable, right? I won't get a deterministic amount of work, I'll have some fluctuations. And there are two really important kind of results in this world. So the first one is the so-called Dzerzhinsky equality, which says, well, I can have fluctuations of work and I can actually have statistical violations of the second law, but those violations are bounded and they're exponentially suppressed. So this is a very famous result from the 90s. And there's a kind of a slightly stronger version of it, which came soon afterwards, which is called the Crookes fluctuation relation, which says, well, okay, if you look at these fluctuations in the forward process and I consider what would happen if I actually went backward and tried to kind of recover my work, that these fluctuations have to satisfy this very nice relationship, right? So these are two canonical results. And so what we asked ourselves is, well, what happens if, again, I'm going to be an agent doing a thermodynamic task, have an attitude towards risk, kind of how much would what would be how would I value this process, basically, if I have an aversion to risk? And so this led us to introduce what we called the certainty equivalent dissipated work. And now we had to switch actually to the second utility function. It turns out to get nice clean results. So we have now an exponential utility. And so we wanted to introduce this quantity to say, well, what is this? It's kind of the value I would give to this process from this perspective. And so we get two results, which I'll show very, very quickly. So the first result is that we get a very nice characterization of this quantity, again, in terms of Arrhenius divergence. So it turns out it's the divergence between this forward and this fictitious backward process. And again, the Renyi parameter is entirely determined by my attitude towards risk. So this again pops out, which is very nice. And this really is a generalization of the second law of thermodynamics, which is kind of cool. So that one we recover when R is 0, and we get back the old result. So we also get a generalization of Dzerzhinsky. So if we look at a slightly different average than in Dzerzhinsky, so we add this R parameter where we add some number into when I perform this average, it turns out that this is actually then the exponential of this certainty equivalent dissipated work, right? So this is brand new. And if I just sub in result 1, I can also express it this way, but the second one is not so important. So again, this is a generalization of Dzerzhinsky. And this one has this funny feature. So you say, do we recover Dzerzhinsky? And we do. And now we recover it when my attitude towards risk is this so-called, is a -1 is the parameter, which is perfectly fine. And that's actually a gambler who would bet on violations of the second law, right? So it kind of tells us something a bit about Dzerzhinsky, I think, kind of explains a bit where this comes from, right? And so with that, it looks like I'm out of time. So I'll leave up my final slide. You can have a look through, and I'll say thank you very much.
Thank you. We do have time for a question. Please.
Thank you for the interesting talk. Could you go back to the page 7? Okay, thank you. So in usual state discrimination, the discrimination, optimal discrimination, the robustness is related through the semi-definite programming. But so in this result, is it the same? So the left hand side and also right hand side is related to through the semi-definite programming or not. So I would like to.
So in this case, we don't, I mean, interestingly, no, there are no semi-definite programs that pop up as far as I'm aware. We didn't need to use it. The other thing which is kind of curious here is that, so actually this holds for every ensemble and every measurement, right? So normally in these results you're referring to, there's also an optimization over games and an optimization over measurements. And here we actually get an equality for all games and all measurements, which is kind of a bit stronger in this sense.
Yeah, thank you very much.
Thank you.
Thanks for a very nice talk. Did you consider the case where you optimize over measurements as well? It seems like a natural.
So you can, of course, you can do it. But I mean, I think then the expression we get isn't any more informative in some. I don't think I learned any. Yeah, we looked at it, but we didn't seem to gain anything by doing the optimization. So it's slightly curious. I don't know quite what to make of this, but it might be that we missed the right way to think about it. But at the minute, we don't need to.
Okay, yeah, I guess if you go with D max, I mean, in this limit, then you would get the quantum divergences and so on, but maybe not for general alpha. So that, I mean, the goal would be that you get some quantum divergences out.
Yeah, so I mean, I've said this on my final slide, but I didn't have a chance to say it. But of course, so far, what we've done is very classical, right? And we got back very classical divergences. I mean, I would love to know, I would love to study, and this is the plan, is to study more kind of natively quantum tasks and see, for example, do they naturally lead to some particular representation of a Renyi divergence? I think that would be really nice if again, it gave us a natural way of arriving at certain quantities. And I'm sure we have to be very careful about how to do that to get to the right answer. I think I would love to do this. It's just a matter of sitting down and doing it.
Okay, thanks a lot.
Thanks, Marco.
Great. Let's thank Paul again. And we currently have now a 30-minute break, and after that, the business meeting. Please attend.